So picture this. You're at a crime scene, but your culprit, it's invisible, it's microscopic, and there are literally millions of potential suspects. That's pretty much the daily grind for a clinical microbiologist. Today, we're going to put on our detective hats and crack the case of an unknown bacteria.
I mean, this is the big question, right? It seems totally impossible. You can't just walk up to a bacterium and ask for its ID. But just like a real detective, microbiologists have this amazing systematic playbook, a whole series of clues and tests that lead them straight to the culprit's identity.
So here's our game plan. We're going to start by splitting up the suspects, and then we'll follow two completely different trails of evidence, the gram-positive and the gram-negative leads. We'll even check out some of the more unusual suspects that try to fly under the radar. And then finally, we'll see how all the clues come together to crack the case. Okay, so every good investigation needs a solid starting point. In microbiology, that first absolutely crucial clue comes from staining. This one single procedure takes a massive list of potential suspects and immediately splits them into two main gangs, and it's all based on one thing: the structure of their cell wall.
The classic technique here is the gram stain. First up, all the bacteria get hit with this deep purple dye called crystal violet. Then we add iodine, which acts as a mordant. You can think of it like glue that helps that purple stain really stick inside the cell. Now step 3 is the most important part, the decolorizer. This alcohol wash will either strip that purple dye right out, or it won't. And finally, a pink counterstain, safranin, is added to give a splash of color to any bacteria that lost that first purple dye.
And this is where we get our two gangs. The gram-positive bacteria, they have these thick cell walls that trap that purple-iodine combo, so they stay a really deep purple. But the gram-negative bacteria have thin walls, so the decolorizer just washes the purple right out, and they end up grabbing that pink counterstain instead. And boom, just like that, every suspect is now on either Team Purple or Team Pink. Our investigation has its first huge break.
All right, let's head down the purple trail first. We know our suspect is gram-positive, but you know what? That's still a massive group of bacteria. We're going to need a few more clues to narrow this thing down.
So our detective is looking at a purple suspect under the microscope. The next question is actually pretty simple. What's it look like? We're really looking for two things. First, its shape. Is it a little sphere, what we call a coccus, or is it a rod? And second, its arrangement. Does it fly solo, or does it hang out in pairs, chains, or little clusters?
And this, right here, is the next big aha moment in the case. If we see our cocci huddled together in these little grape-like clusters, our prime suspect is Staphylococcus. If they're lined up in neat chains or pairs, it's almost certainly Streptococcus. And here's the real game-changing test to tell them apart for sure, the catalase test. We just add a drop of hydrogen peroxide. If it bubbles up like crazy, it's positive. That's staph. No bubbles? Negative. That's strep. See? Another fork in the road, and a ton of suspects just got eliminated.
Okay, so we've got our culprit. It's a member of the Staphylococcus gang. But this family's got a few different members, including the really infamous S. aureus. So how do we pinpoint the most dangerous suspect in the lineup? Well, you guessed it. We need another test. The key test for this is called coagulase. Now, Staphylococcus aureus is coagulase positive, which means it can literally make blood plasma clot. This is a huge red flag because it uses this trick to build a little shield around itself, basically creating a hiding spot from our immune system. The other common staph species can't do that. For those guys, we use a little antibiotic disc called novobiosin to tell them apart. S. epidermidis is sensitive to it, while S. saprophyticus just shrugs it off. So the point is, with just a few smart, targeted tests, we've gone from millions of possibilities all the way down to a specific ID.
All right, hit the rewind button for a second. What if our first stain came back pink? Well, now we're on the gram-negative trail, and this investigation is about to take a totally different, but just as interesting turn.
The playbook's pretty similar here. We start with the shape. If we see gram-negative cocci, and they often pair up and look like tiny little kidney beans, our next move is the oxidase test. This is a super fast test that looks for a specific enzyme. For our main suspects here, like Neisseria and Moraxella, a quick color change to blue or purple tells us it's positive, and we know we're on the right path. Okay, with our suspects cornered, we basically interrogate them by checking out their appetite. It's all about which sugars they can eat or ferment for energy. Think of it like a dietary lineup. Neisseria gonorrhea only has a sweet tooth for glucose.
Its more dangerous cousin, Neisseria meningitidis, can handle both glucose and maltose. And then you've got Moraxella catarrhalis, which is the picky eater of the group. It doesn't ferment any of them. These unique little metabolic fingerprints are what give them away every time.
But what if our pink suspect is a rod? I mean, this is a huge, super common family of bacteria. Luckily, there's this one incredible powerhouse of a tool that gives us a ton of information all at once, the triple sugar iron slant, or TSI for short. This one little tube of agar tells a whole story. It has 3 different sugars in it, glucose, lactose, and sucrose, plus an iron indicator. By looking at the color changes, we can learn so much. If the whole tube turns yellow, what we call A/A, it means the bacteria ate all the sugars, like E. coli does. If only the bottom part turns yellow, or K/A, it only fermented the glucose, like Salmonella. And if it pretty much stays the same color, or K/K, it's a non-fermenter, like Pseudomonas. One test, 3 totally different stories. It's so efficient.
Okay, now for the really sneaky cases. Some bacteria are just masters of disguise. They don't play by the rules of the gram stain, and they force our microbiology detectives to pull out some really specialized tools to unmask them.
Let's meet the 3 main gangs of these rule breakers. First, you've got the waxy mycobacteria, which wear this kind of biological armor. Then there are the super thin, spiral-shaped spirochates that are just too stealthy to see easily. And finally, mycoplasma, the ultimate ghost suspect, which doesn't even have a cell wall, the very thing our main test is designed to look for. So mycobacteria, like the one that causes tuberculosis, have a cell wall that's just packed with this waxy stuff called mycolic acid. You can think of this wax as a raincoat, and it just stops the gram stain dyes from ever getting inside. To actually see these guys, we need a special procedure called an acid-fast stain, which uses heat to literally force the dye through that waxy layer. Then you have the spirochetes. These bacteria, like the one that causes syphilis, are shaped like these long, thin corkscrews. But they are so incredibly slender that they're basically invisible under a regular microscope with normal stains. To spot these super elusive suspects, detectives need a special tool called a dark field microscope, which makes the bacteria light up like little stars against a totally black sky. And finally, the ultimate weirdo of the bunch, mycoplasma. It's not that its cell wall resists the stain. It doesn't have a cell wall at all. So the gram stain literally has nothing to stick to. Instead of staining it, we have to identify it by how it grows. When you culture it, it forms these tiny little colonies that have this classic inverted fried egg look. It's a dead giveaway. So, we've followed the purple trail, we've chased down the pink trail, and we've even managed to track down the most unusual suspects. Now it's time to see how all these different clues come together to definitively crack the case.
The whole process, when you step back and look at it, really works like a giant funnel. You start at the top with millions of possibilities. The gram stain immediately cuts that number right in half. Then, looking at the shape and arrangement funnels it down even further. And finally, just a couple of very specific biochemical tests pinpoint the exact identity. It's this beautiful, logical sequence of deduction.
And that really gets to the heart of it, doesn't it? This isn't just about running random tests. It's about asking the right questions in the right order. Every result, whether it's a color change, a shape under a microscope, or some bubbles in a tube, is a piece of the puzzle. It's a clue that brings the detective one step closer to the truth. But, you know, the story doesn't just end here. Bacteria are constantly changing. They're always evolving new ways to resist our drugs and new tricks to survive. So it really makes you wonder, as our microscopic adversaries keep evolving, what kind of new techniques and technologies will the next generation of microbial detectives need just to stay one step ahead?